Hello friends. So today we are going to solve the questions from the year 2005, and there are total 5 questions from this particular year. So in the first question, it states that a convex lens is in contact with concave lens. The magnitude of the ratio of their focal length is 3/2 and their equivalent focal length is 30 centimeter. What are their individual focal lengths? So we are given that they have a ratio as well as their equivalent focal lengths are given to us. So we assume that for convex lens, let us suppose that focal length is given as f1, and for concave lens, that is given as f2, and their ratio, respective ratio, is given as 3/2. Okay. So we can say that our f1 upon f2 will be equal to 3/2, and obviously we can write this as with a negative sign, and this will be giving us, we can just manipulate it, that our f2 is equal to minus 2/3 times f1. Now we come to the equivalent part. This was the ratio part, and then the equivalent part. So we have the equivalent focal length let us suppose that is given as f. So we can write 1/f is equal to 1/f1 plus 1/f2. f2, and the equivalent is given as 1/30, and we write 1/30, and in place of f2 we are going to substitute the f1. Therefore we get this as 1/f1 plus 1 this will be minus 2/3 times f1. So solving this will be giving us that f1 is our 15 centimeters, and we already know the relationship between f1 and f2. So f2 will be equal to minus 2/3 times 15, and this gives us as minus 10 centimeters. Therefore our convex lens is having a focal length of 15 centimeter, and concave is having a focal length of minus 10 centimeters. So therefore, so we have this as minus 10 and minus plus 15. So option number B is the correct option. Option B is correct. Come to the second question, and here it states that in Young's double slit experiment, intensity at a point is 1/4 of the maximum intensity. The angular position of this point is. So we are given that intensity at any point is 1/4 of maximum. You can say that intensity at a point, if that is represented as I, then this I will be equal to 1/4 of I max. That is our maximum intensity. And we need to find out the angular position. And for the angular position, we are going to find out first of all what will be the, you can say, the difference, phase difference rather. So we can say that our phase difference and we can use the intensity formula, and we know that intensity, which is our I, is equal to our I max and cos square phi by 2. And we already know relationship between I and I max. So therefore we can write this as 1/4 of I max is equal to our I max cos square phi by 2. I max and I max cancels out, and this gives us that cos square phi by 2 is equal to our 1/4, and this gives us that cos of phi by 2 will be equal to plus minus 1/2. And therefore if we solve for phi by 2, or we can say phi, so we get our phi will be either equal to 2 pi by 3 or it will be equal to 4 pi by 3. And we can consider for the smallest positive solution as phi is equal to 2 pi by 3. Now we can use the relationship between the phase difference and path difference. Relation between phase difference and path difference. And that is our phi is equal to 2 pi by lambda multiplied by our delta x, and we substitute value of phi. This gives us 2 pi by 3 is equal to 2 pi by lambda multiplied by delta x, which gives us 2 pi and 2 pi goes away. So from here we get our delta x is equal to lambda by 3. And we know that the path difference is equal to d sine of theta. We know already that delta of x is equal to d sine of theta, and we need to find out theta, that is the angular. So we substitute, this will be equal to lambda by 3 is equal to our d sine of theta. This giving us that sine of theta will be equal to lambda divided by 3d, and gives us that theta is equal to sine inverse lambda divided by 3d. So therefore the option number C is the correct option. Option C is come to the next question, and here it was also asked in the year 2005, and it states that a container is filled with water, refractive index 1.33, up to a height of 33.25 centimeters. A concave mirror is placed 15 centimeters above the water level, and the image of an object placed at the bottom is formed 25 centimeters below the water level. The focal length of the mirror is. So here the total height of the water is about 33.25, and you can say mirror is placed at a height 15 centimeter above the level of the water, and it says that the image is formed at a height of 25 centimeter, or we can say at a depth of 25 centimeter from the top. So this question is basically you can say related with the apparent depth and the real depth. So we are already given that the refractive index, that is our mu, is our 1.33, and the height of water in the container, let us suppose that is given as HW, that is given as 33.25, and we are also given distance of mirror above the water level. Distance of mirror above water level, and let us suppose that we write a dm, which is given as 15 centimeter, and we are also given that the distance of image below the water level. Distance of image below water level, and let us call that as d prime I, and that is about 25 centimeter. So first of all, we are going to find out the apparent depth of the object. Apparent depth of object. And we can say that the real depth of the object is the height of the water. So we can say that real depth of object is our height of the water. Height of the water. Therefore, we can write that the depth of water, let us suppose object is given a dO, and then this will be equal to HW, which is equal to 33.25. Therefore, the apparent depth of the object, that is our dO prime, this will be equal to the actual depth of the object and divided by its refractive index of the water. So we simply substitute the values. Our dO prime will be equal to 33.25 divided by 1.33. This gives us, it will be coming as 25 centimeters. Now we can easily find out what will be the object distance from the mirror. So object distance from the mirror, and that will be equal to sum of the distance of mirror above the water and apparent depth of the object. So that we can say if that is written as u, then this u will be equal to dm plus do prime. So we have this as 15 plus 25 giving us as a 40 centimeters, and we know that the real depth of the image is given as 25 centimeter. Yeah, so we have to find out the apparent depth. Okay, this is our depth of the image, and that is given to us as a 25 centimeters. So now we can find out that the apparent depth of the image that is our di prime will be equal to depth of the image divided by its refractive index. So we get that di prime will be equal to 25 divided by 1.33, and this comes approximately is equal to 18.8 centimeters. I think closest is our 20 centimeter. So we can write the option C is the correct. Oh, sorry, we need to find out the focal length, my mistake. Okay. And we found out the apparent. Now this is going to help us to find out the distance of the image. So we can say image distance from the mirror that is our V. So we can write our V will be equal to dm, that the distance of mirror above the water, and apparent depth of the image, that is our di prime. So we get the 15 plus 18.8. This will be giving us close to 33.8 centimeters. And this is a concave mirror. So therefore, you can say for a concave mirror, we can write a V will be equal to minus of 33.8. Now we are going to use the mirror formula to find out the focal length. That was our ultimately required. So 1 upon f is equal to 1 upon u plus 1 upon v, and this gives us 1 upon 40 plus minus of 33.8. So we get that our focal length, that is of f, will be approximately equal to 18.3 centimeters. So this is the focal length which was actually required. So the option number C is the correct one. Okay. Option C is correct. So we come to the next question, and it states that AB and CD are two slabs. The medium between the slab has a refractive index of 2. Find the minimum angle of incident at Q so that the ray is totally internally reflected by both the slabs. So here we are having two slabs, one that is denoted as A and B, second that is denoted as C and D, and we have ray which is being total internally reflected at 2 points, at Q and at other point. Let us suppose this point is our Q prime. Okay, and we need to find out the minimum incidence angle at Q. So we can divide this question into two parts by considering these slabs individually. Okay, so let us consider this as slab 1 and this as slab 2. So for slab 1, we can draw the figure approximately. So this is our AB. Refractive index is given as square root of 2, and here refractive index is 2. Let us call this as mu1, let us call this as mu2. And the ray of light is incident at this particular point that is given as Q. Let us suppose angle of incident is I. So obviously square root of 2, that is our 1.414, and our 2, that is our so mu2 is greater than mu1, and we are mainly interested in the finding the critical angle. So we can say for critical angle C, or critical angle C, we can write that mu2 multiplied by sine of C will be equal to mu1, and we can write that sine of 90, and that is equal to, and we can write from here that mu2 is our 2, this is our sine of C, and mu1 is our square root of 2, sine 90 is our 1. So therefore we get from here that our C will be equal to 45 degree. Okay. And so it means we need a total internal reflection at AB. So we can say for total internal reflection at AB, the angle of incident should be greater than critical angle, or we can say the incident angle should be greater than our 45 degree. Okay. And this is for only slab that is consisting of AB. Now we come to part slab 2. So we can write that for slab 2, we can once again draw an approximate figure. So this is our CD, and here refractive index is given as square root of 3, and here refractive index is our 2. So let us call this as 3, and this was our 2, and ray of light is somewhat incident in this way. Okay. And this is our CD. So once again we can use critical angle, and in this case let us call that critical angle as C prime. So we can say critical angle is our C prime. Therefore we can write that our 2 sorry, not 2 but mu 2, sine of C prime will be equal to over mu 3, and this is sine of 90, and mu 2 is about 2, and this gives us C prime mu 3 is of square root of 3 and multiply by 1. So from here we get that our C prime is equal to 60 degree. So which means that for total internal reflection at CD, our angle of incidence, that is I, or we can call this I prime for the sake of differentiation, should be greater than our C prime, or that is our I should be greater than our 60 degree, I prime rather. So therefore, making comparison between two values of I, one is our 45 degree and another one is our 60 degree, we can easily see that the minimum angle for which the total internal reflection is going to take place at both the slabs will be equal to 60 degree. So you can say that minimum angle of incidence for total internal reflection to take place on both slabs is our 60 degree. So we come to the next question. In this question, it says that a ray of light is incident on a prism ABC of refractive index square root of 3 as shown in figure. Based on this, we have two questions. Find the angle of incident for which the deviation of the light ray by the prism ABC is minimum, and part B, by what angle the second identical prism must be rotated so that the final ray suffers net minimum deviation. So here we are basically having two prisms. One prism is our ABC and another prism is our CDE, and both these prisms are, you can say, identical, and the respective angles are given as 60 degree, and the angle between two prism is also given as 60 degree. Okay, so this basically is forming somewhat like a equilateral triangle. Okay. And first of all, we have to find out the angle of incidence such that there is a minimum deviation from the prism ABC, and we know the basic formula for that. Okay, so we start from there only, and so we know that refractive index mu is equal to, we have our sine of A plus delta divided by 2, and this is sine of A by 2, where A is the angle of the prism and delta is the deviation. And we are given that the angle of the prism is of 60 degree, and we have a refractive index of square root of 3, and we are going to substitute the respective values. So we can write of square root of 3 is equal to, we have this is sine of 60 plus deviation which we require to be minimum divided by 2, and this comes as sine of 60 divided by 2. So if we solve this, we are going to get that our delta minimum will be equal to 60 degree. So it means the minimum deviation, the angle of incidence should be 60 degree to have a minimum deviation. One second. We have to find out the angle of incidence. Okay. So that the deviation is minimum. So this is our side AB, and we have incident ray something like this, and normal, so it will be bending like this. So this is our I and this is our R. And for minimum deviation, we also know that after the refraction, this light ray is parallel to the, you can say, base of the prism. So we can call this as R1, and here we can call this as R2, and this is our A. And we already know the relationship that our R1 plus R2 is equal to A, and at minimum deviation this R will be equal to A by 2, and we also know that the relationship is our I plus angle of emergence, and one second. Yes. So from here we know already the angle of the prism, so I can say my this R will be equal to my R2 and will be equal to A by 2, that is 60 by 2, and that comes as 30 degree. And therefore we can use Snell's law. Let us suppose this is our I1 and refractive index here is our mu2 and this is our mu1. So let us call this as point P. You can say Snell's law at P, we get this as mu1 sine of I1 is equal to mu2 sine of R2. Mu1 is our air and mu2 is given to us as square root of 3. Yes. So we can write this as 1 multiplied by sine of I1 is equal to square root of 3, and here we have sine of 30. So this gives us that sine of I1 is equal to square root of 3, and we have sine of 30, that is our 1 by 2. So this comes as square root of 3 divided by 2, which gives that the angle of incidence will be equal to 60 degree. Here I found. Anyways, there was slight confusion on my part. So this is the first part. And the second part, it says that by what angle the identical prism must be rotated so that the final ray suffers the net minimum deviation. So one thing is very clear, that we have to arrange this DCE such that this DC is almost merging with our BC, like a parallel line. Okay. So it means what we want, that our final figure in which the DCE is rotated should be like this. So we want that this is our triangle, our A, B, C, and we had our triangle as this is our DCE, and we want to rotate it in this direction, that finally the B, one second, okay, so this was B, not A. So this is our B and this is our A. Now we want that our B and D should be one common point, and ultimately we are going to get this triangle like this. It should be merging in this way. Okay, so D and C will be along this line, and ultimately E will be somewhere here, and this will be a final figure. Okay. So this will be getting us E. So we can say, and the angle between the two is given as 60 degree. So it means the rotation has to be of 60 degree. So we can say that triangle DCE should be rotated anticlockwise through 60 degree so that the net deviation, so that the final ray suffers minimum deviation, so that final ray suffer minimum deviation. So these were the, that's all. So these were the questions that was asked in their year 2005. So this completes all the questions. Thank you.